So in this video, we'll do some problems related to directional derivatives and the gradient of a function. So we're going to work through some examples. This problem says to use theorem 13.9 to find the directional derivative of the function in the direction of the unit vector. Theorem 13.9 you can find in your book, but I'm going to show you how to work this out. So the function of x and y is y over 6x plus y. The point is 2, 0, and theta is negative pi over 6. So first of all, the unit vector u, it says here, is cosine of theta I cap plus sine theta j cap, and we're given a theta. So let's find u. U is equal to cosine of minus pi over 6 I cap plus sine of minus pi over 6 j cap. And we can think about those values. Minus pi over 6. So the cosine is going to be square root of 3 over 2, and the sine minus 1/2. So then u is square root of 3 over 2 I cap minus 1/2 j cap. So that's first things first. Now we know that our directional derivative is going to be the gradient and the dot product of the gradient with this unit vector that we just found. So let's find the gradient of our function. I'm going to remind us. d sub u of f, meaning the directional derivative of f in the direction of u. We're going to find our gradient of f and dot that with u. So the gradient of this function, we need the partial derivative with respect to x and y. So the gradient is going to be the vector that is made up of del f del x and del f del y. Or we can write that as f sub x I cap plus f sub y j cap. So let's take these partial derivatives. The partial with respect to x. Now remember, I'm going to treat y as a constant. So basically we've got a constant on top, and on the bottom we have 6x plus y. So I would like to think of this as y, a constant, times 6x plus y to the minus 1, and just use the power rule. So that's going to be minus y times 6x plus y to the minus 2, and then I need to multiply by the derivative of the inside, which is 6. So that's going to be minus 6y over 6x plus y whole squared. Now, of course, that's not the only way to find this derivative, but I like that way. Now let's find the partial with respect to y. In this case, we're treating x like a constant, but if we look at our function, we have y on both the top and the bottom, so we're going to need to use the quotient rule. Move this down just a little. Del f del y. So that'll be the bottom, 6x plus y, times the derivative of the top, but the top is just y, so the derivative is just 1, plus the top, y, times the derivative of the bottom, and in this case, that's just 1 as well. And of course, that should be minus y, because I'm doing the quotient rule. So the bottom times the derivative of the top, minus the top times the derivative of the bottom, all over the bottom squared. And that gives us 6x over 6x plus y whole squared. So we found our two partials. That means we get to say that the gradient of f is going to be minus 6y over 6x plus y whole squared, I cap, plus 6x over 6x plus y whole squared, j cap. Okay, so that's one piece of the puzzle. And we have our unit vector, which was square root of 3 over 2 I cap plus minus 1/2 j cap. We need to take the dot product. And finally, we're going to evaluate it at the point 2, 0. So let's take the dot product. The directional derivative of f in the direction of u is going to be minus 6y over 6x plus y whole squared, dotted with square root of 3 over 2. Rather, I should say multiplied with square root of 3 over 2, plus 6x over 6x plus y whole squared, multiplied by negative 1/2. So that's minus 3 square root of 3y over 6x plus y whole squared, minus 3x over 6x plus y whole squared. And I want to evaluate that at the point 2, 0. So the directional derivative of f in the direction of u, evaluated at the point 2, 0, is minus 3 square root of 3 times 0, which of course will be 0 over 6x plus y whole squared, minus 3 times 2 over 6 times 2 plus 0 whole squared. This should also be that, but of course it doesn't matter because this term is going to be 0. Nonetheless, let me write it. So that would be 6 times 2 plus 0 squared. And so it works out to be 6 on top, negative 6 on top, and on the bottom 144. Minus 6 over 144, and that's minus 1 over 24. So the answer to my question, which asked me to find the directional derivative of the function at the point P in the direction of a specific vector, is going to be minus 1 over 24. Okay, let's do another problem of this type, because these problems can be asked in multiple ways, where you actually have to find that unit vector. So in this case, we were given the angle that the vector makes with the y-axis, with the x-axis, and we just used our unit circle to find a unit vector. In the next problem, this is a similar problem. We want to find the directional derivative at a point P in the directed, so in this case we're given a vector, but it doesn't look like it's a unit vector. So instead of being given the angle, we're given the vector. Okay, but it's the same idea. So let's first find the unit vector, u. So u is going to be v divided by the magnitude of v. So the magnitude of v is the square root of 16 squared plus 1 squared plus minus 1 squared. 16 squared is 256. 256 plus 2 is 258. So the magnitude of v is 258. That means that our vector u is going to be 16 divided by the square root of 258 I cap plus 1 divided by the square root of 258 j cap minus 1 divided by the square root of 258 k cap. So that's one piece of our puzzle. We needed a unit vector. And we know we're going to find the gradient and then dot them. So our function is xy plus yz plus xz. So we want to find the gradient. That means we need the partial derivatives. The partial of f with respect to x. From the first term xy, I'm going to get y. I treat y like a constant. I have 1 power of x, so the derivative is y. And from the second term yz, I have no x, so I get 0. From the third term xz, I get z. So the partial with respect to x is y plus z. Do the same thing for the partial with respect to y. From the first term I get x. From the second term I get z. From the third term I get 0. So it's x plus z. And the partial with respect to z. From the first term I get 0. From the second I get y. From the third term I get x. So it's y plus x. Okay, so I have my partial derivatives. And I know that the gradient is going to be the partial with respect to x, I cap, plus the partial with respect to y, j cap, plus the partial with respect to z, k cap. So that's the next piece of my puzzle. I need to find the dot product of these two vectors and then evaluate it at the point given. Or rather, I can evaluate at the point given and then find the dot product. So that seems like it should be a little more straightforward. So the gradient of f at, of course, this should be x, y, and z here. Erase. So this should be f of x, y, z. All right. See, did I do the same mistake anywhere else? Not yet. Okay, so this will be gradient of f evaluated at 8, 9, and negative 8. I can just directly substitute those in. So I get 9 minus 8 I cap. So just I cap. And then I get 8 minus 8 j cap, so 0. And for k cap, I have 9 plus 8. So 17. That is I cap plus 17 k cap. Now I'm going to do the dot product. So I need to take the dot product of this value this vector that I just found with u. So that's going to be 1 times 16 over square root of 258 minus 17 over square root of 258, or 17 times 1 over square root of 258. So that's minus 1 over square root of 258. If you want to rationalize, you can. So we can say this is minus 1 over square root of 258, or we could say it's minus square root of 258 over 258. Doesn't matter. Actually, I'm not sure if it matters in web assign, but in reality it doesn't matter. And that is the answer to the question. So as you saw, it's quite similar to what we did in the first question, except in the first question we were just given an angle and we used that to find a unit vector. In the second question we were given a vector and we used that to find the unit vector. You could also be given 2 points and asked to just find the vector that connects those. So that's one other version of this problem. All right. So here's one other problem, which first just asks us to find the gradient of the function at a given point. We know how to do that. We just find the partial derivatives. Then it asks us to find the maximum value of the directional derivative at the given point. So we'll talk about that and what that means. But first, let's take the gradient of our function h of x and y. We know that means I need to find the partial with respect to x, should be dh, the partial with respect to x, and then the partial with respect to y. So del h del x. The function is 5y times the cosine of x minus y. When we're talking about the partial with respect to x, we're going to treat y as a constant. So this is basically like 5y is a constant. That means I just write it down. And what I'm really taking the derivative of is the cosine of x minus y. Derivative of cosine is minus sine of x minus y. I need to multiply by the derivative of the inside, but the derivative of the inside is just 1 with respect to x. So this is just minus 5y sine of x minus y. Then I'll find the partial with respect to y. But since y appears in both terms, I need to use the product rule. So I'll do 5y times minus sine of x minus y. Then times the derivative of the inside gives me 1 more minus, plus cosine of x minus y times 5. So that's 5y sine of x minus y plus 5 cosine of x minus y. So now that I know my partial derivatives, I can write them as the gradient. So the gradient of the function h of x and y is going to be minus 5y times sine of x minus y times I cap plus 5y sine of x minus y plus 5 cosine of x minus y j cap. All right. So I have my gradient. And then I'm asked to find the gradient at a point. So I'm going to evaluate this at the point 0 pi over 3. So gradient at 0 and pi over 3. That's minus 5 pi over 3 times the sine of 0 minus pi over 3, I cap, plus 5 pi over 3 times the sine of 0 minus pi over 3, plus 5 times the cosine of 0 minus pi over 3, j cap. And that gives me, well, the sine of negative pi over 3 is negative square root of 3 over 2. Negative and negative cancel. So 5 pi over 3 times square root of 3 over 2. I cap. And then here, this is going to be negative because the sine of negative pi over 3 is negative square root of 3 over 2. Negative 5 pi square root of 3 over 2. Plus, then the cosine of negative pi over 3 is 1/2. So plus 5 times 1/2, j cap. And just combining my fractions, that's 5 times square root of 3 pi over 6 I cap plus 5 over 2 minus 5 square root of 3 pi over 6 j cap. Just for good measure, let's go ahead and make this a common denominator here. So instead of 5 over 2, maybe let's write 15 over 6. Okay. So that answers part of my question, which is the gradient of the function at this point is given by the vector 5 square root of 3 pi over 6 and 15 minus 5 square root of 3 pi over 6. So that's my vector notation. Then the second part of the question asks me to find the maximum value of the directional derivative at the point. So a couple of things we want to know. The gradient tells us the direction of the maximum change. And the maximum value then is the magnitude of the gradient at that point. So the gradient just tells us the direction of maximal change. The magnitude of the gradient gives us that maximum value for the directional derivative at that point. So we need to find the magnitude of the gradient of h at 0 and pi over 3. And we have this vector that we want to take the magnitude of. So it would probably be a good idea to go ahead and pull out 5. And then I'm going to do, of course, the square root of the first component squared. So big square root of square root of 3 pi over 6 squared plus 15 minus 5 square root of 3, and I'm sorry, I took out the 5, so that's going to be 3 minus square root of 3 times 5 over 6 squared. We'll simplify that. So that's 5 outside the square root, and inside the square root. Square root of 3 times square root of 3 is 3. 3 pi squared over 36. And then here, we're going to have 3 times 3 is 9. Minus 3 square root of 3 pi. I get that term twice. So minus 6 square root of 3 pi. And then plus 3 pi squared. That's also over 36. So I still have 5 in front. Square root of 36 is 6, so I can just say this is 5 over 6. And inside my square root, I have 3 pi squared plus 3 pi squared, that's 6 pi squared, minus 6 square root of 3 pi, plus 9. And whatever that value is, that should be the maximum value of the directional derivative at the given point. So let's write that in. That's 5 over 6 times the square root of 6 pi squared minus 6 square root of 3 pi plus 9. And that answers the question. The next problem asks us to find the normal vector to the level curve, f of xy equals to c at a point P. So let's pause here and remember that the gradient is normal to level curves. So if I'm looking for a normal vector, the gradient vector should be a good candidate. So let's first look at the level curve. The level curve in this problem is to take my function 9 minus 10x minus 2y and set it equal to c equal to 9. So set it equal to 9. So my level curve is actually minus 10x minus 2y equal to 0. So it seems like it's going to be a line. And we're looking for a normal vector. So let's find the gradient of the function. The gradient of f is going to be the partial with respect to x, which is just minus 10 times I cap. And the partial with respect to y is minus 2 times j cap. So that is a normal vector to the level curve. And lastly, I'm asked to evaluate it at a point. The point I'm given is 0, 0. But it's still negative 10 I cap minus 2 j cap because I don't have x or y in my problem. So the answer to my question is minus 10 I cap minus 2 j cap.